Hello to whoever is watching this video. Here I am going to present you our project that we made for our control system theory course. The name of our project is Inverted Pendulum and Cart. This project is actually a pretty common one. If you are taking control system theory course or any control system course, there is a big possibility that you will come across this problem. This problem actually helps us to understand the effect of controller. So the basics of this project is usually used in quadrocopter, balancing cart and other tasks that require stabilization. So this is a practical demonstration of the system. Here we go. We have applied a force and the pendulum has returned to its inverted position. So now let's look at our animation. Okay. Here we go. So you can see a pendulum is connected to a card in the downward position. First, we swing up the pendulum in the inverted position. Okay, it will take a while. So let's wait for some time. You can see it's swinging up. Okay, you can see it has finally swung up to the inverted position. Now, if we apply an impulse force on the system, what we expect to happen is that the pendulum to go back in the downward position, but it doesn't actually happen. Because of adding a controller, the pendulum stays in the inverted position. Okay, now let's see if it happens or not. Let's apply an impulse force. Okay, you can see the pendulum is oscillating. And it has returned to its inverted position. Now let's apply a force on the opposite direction. Okay, now the same thing happens. It comes back to the inverted position. And now notice another thing. Practically there will be some environmental noises. So because of that, the pendulum won't be completely stable. There will be a slight vibration in the system. You can see there's a slight vibration. So we try to show that in our animation too. If you see closely, there's actually a slight vibration. You see, it's not completely stable. Okay, now to do that, we have simply added a noise generating block in our simulink diagram. Here we go. This is the one. And okay, now initially we have chosen some suitable values for Kp, Ki and Kd, and we can see the system is fairly stable. So in our animation we can change these values and observe the responses on the system. So at first, if we make Kp nearly 0, theoretically the system is supposed to become unstable. So let's see if it happens. Let me apply a force. Here we go. It has become completely unstable. You can see the oscillation never stops. So if you make Kd nearly 0, the settling time is supposed to be very high, which means the pendulum will oscillate for a long time before becoming stable. Let's see if it happens or not. You can see the pendulum is oscillating. You can see that the oscillation is actually decreasing, but it is taking a very long time for the pendulum to return to the invert position. So we have plotted the angle and the impulse forces to give you a clear idea. Let's look at it. Here we go. These are the forces that we applied. So this is the swing up process. You can see the pendulum has become stable at 180 degree, and you can see that there are slight vibration. If we zoom in, it will give you a clear view. You see there are vibrations. Okay, now this part shows the angle of the pendulum when Kp is nearly 0. You can clearly see it's completely unstable, and this is actually the part where Kd is nearly 0. You can see that the oscillation is slowly decreasing, and after a very long time it will become completely 0, and then the pendulum will be stable at 180 degree. Okay, now let's go back to the animation. We haven't yet seen the effect of Ki. Let's see what happens if Ki is nearly 0. Let me just start the animation again. Okay, so if we make Ki nearly 0, what is supposed to happen is that the pendulum won't oscillate much before becoming stable at the upright position, and there will also be a steady state error, which means that the pendulum won't be stable at exactly 180 degree. Okay, it might become stable at a value higher or lower than 180 degree. So let's see if it happens or not. Okay, the pendulum has swung up. Now let's make Ki nearly 0. Okay, here we go. We apply a force. You can see the pendulum has become stable, but it's not exactly in the upright position. If you see the graph, it will become clear. Okay, here we go. If we zoom in, see, it's not stable at 180 degree. It has become stable at maybe nearly 185 degree. Okay, and these are the vibrations due to environmental noises. Okay, now let's go back to the simulink diagram. Let's go to the simulink diagram. Okay, I'm sorry. Here we go. Okay, now it may seem a bit complicated, but this complexity occurred because we had to connect the VRML world and the MATLAB simulink diagram. The main basic block diagram is actually quite simple. Here it is. This is the one. So you can see that there are two transfer functions. One is for the pendulum angle, and the other is for the position of the cart. So this angle is fed back, and the error angle must be 0. So this error is sent to the controller. Now a force is applied, and the ultimate force, this error is added to the force, and the output is applied to the plant. Now how did we get these transfer functions? This is actually the basic of the theory. There are three forces. One of them is due to acceleration, the force that we applied. One of them is a force due to reaction. This works here, and another one is the force due to friction. So to avoid detail, we didn't show you how we derived these equations. Actually, we can these are very common equations, and you can search the internet, or you actually might see the book on control system written by Dorff. So from these two equations we get the transfer functions. Again, to avoid details, we didn't show you the derivation. Actually, it's not that hard. If you use linearity approximation to avoid complexity, which means that from simple trigonometry, you can see that for small angle, sin theta is equal to theta and cos theta equals to 1. Then this derivation becomes fairly simple. You can search net also for to see how we derived these equations. So notice one thing, we have used linearity approximation, but the system is actually non-linear, so there is actually some differences from the practical system in the animation. If you can include the non-linearities, your animation might improve actually, but we have just avoided it to avoid complexity. Now this is the main basic block. Here are the transfer functions. We have used the transfer function block of simulink, which you can get like this. Go to simulink library browser, then continuous option, then this is the transfer function block. So let me show you what we did. We just stored the numerator values here and the denominator values here. So you can see that we have used some constants here. So for how did we define this constant? So this is actually fairly simple. Go to file, then model properties, then model properties again, then callbacks, then init function. Here we go. This is the mass of the cart, mass of the pendulum, friction, inertia, gravity, length, and these are the constants. Okay, this is actually similar to these things, these transfer functions. Okay, now we connected the simulink diagram to the virtual world by using some inbuilt functions: VR sync, VR signal expander, VR source, and demux. Now the output generated in simulink is sent to the virtual world by VR sync and VR signal expander. To send the input from the virtual world to the simulink, we used VR source and demuxes. Now these are the demuxes. Now let me just add this VR source option is found only in MATLAB 2011 or higher versions. We have designed this animation in MATLAB 2014. Now this what do these terminator blocks do? You can see there are two terminator blocks. It is actually this button translation outputs values along x, y, and z, but we only need the values along the x-axis, so we just terminated the values along the y and the z-axis. Okay, now why should we use VR source, VR sync, VR signal expander, and how to make this virtual world has been clearly explained in many YouTube tutorials. For example, we have taken help from this YouTube tutorial, Getting Started with Simulink 3D Animation. It's actually a very good tutorial and helped us a lot. So you can see that we made the MATLAB interactive, so that the user can apply force to the cart and change the values of Kp, Ki, and Kd. To make this possible, we have used a node named plane sensor in the VRML builder. Let's go to nodes, insert, sensor. Here we go, plane sensor. And this plane sensor is actually not visible, but when you place your normal cursor on the location of the plane sensor, a hand-like sensor appears. We wanted this sensor to move only along the x-axis, so we set the y-axis values of this sensor to 0. The maximum position of y-axis is 0 and the minimum position of y-axis is also 0. So now we wanted to move the red button along with the hand-like cursor. So for this we use the route option. This is the one, from sensor translation changed to button translation, which means that if we drag this hand-like sensor, the red button will move along with it. Why we did this? Actually, the distance the button covers, which is the translation of the button, has been used as the force values or the Kp, Ki, and Kd values in their respective slides. So now the force that we applied here has to be an impulse force. For this we used a block named embedded MATLAB function, and wrote a code there. This is the one. Okay, now we are coming to this function later, and first let me tell you what would have happened if we haven't used this function. As we use the button's translation as impulse force, we have to drag the button to a certain position and drag it back to 0 as soon as possible, because it has to be an impulse force. So as you can understand, practically it will definitely take some time to do this, but you know, impulse works for a very short time. So to make it more like an impulse, we used the is active option of the sensor. This is the one. This is active option will be 1 when we click the button, the red button, and it will be 0 when we unclick it. So let's look at the code. This is the one. So you can see that when is active is 0, the button's translation becomes 0 instantly. Let me show you what actually happens. Here we go. I'm sorry. See? Let me show you again. It goes instantly to 0 whenever we unclick the red button. Okay, now so what we did here is that we reduced the time of dragging the button and made it more like an impulse force. So at the beginning of the animation, you can see the pendulum is swinging up slowly to the upright position. What we did here is that we have applied acceleration until the pendulum's angle was 180 degree, and we added this angle to the error angle. Here we go. This is the one. So this was our project, our animation project. We tried to make our animation as practical as possible, but as you know, we used linearity approximation for this non-linear system. So there is definitely some differences from the practical system. Thanks for your patience. I hope this tutorial helps you.